Hello, Gregory Carlson here for College Algebra, section 2.6, and we're going to talk about continuity, which is a calculus topic actually. And you'll remember in the last section we were looking at the different parent graphs, and most of them behaved very nicely. They had nice smooth curves, but some of them got chopped up. They either had a jump that they had to do or something else, which brings us to this idea of continuity. So I'm going to give you the college algebra simple definition, but then I'm going to also give you the calculus definition of continuity, just so you can see what it is. So here's what continuity means. A function is continuous if you can draw its graph without lifting your pencil. And I know that definition sounds kind of goofy, but it's a great definition because that's really what continuous means. So a function is continuous if you can draw its graph without lifting your pencil. So for our purposes, that's going to be the definition of continuity, but let's give us the calculus definition as well. So here's the calculus definition of continuity. And the calculus definition is a function is continuous if for all points, which I'll just call C, if for all C, so for every point on the graph, we need three things to be true. First, we need f of C to exist. In other words, there has to be a point there. There has to be a point. The limit as x approaches C has to exist. In other words, the graph needs to approach the same value from both directions. And finally, we need that limit to equal the actual point. And so in other words, when those two when those two approaching lines come together, they actually need to equal the point that's right there on the graph. So that's the calculus definition. F of C must exist, the limit must exist, and the limit has to equal the point. But for our purposes, it's good enough just to have this, as long as you can draw it without lifting your pencil. So let's look at two types of things that are not continuous. The first type is a removable or a point discontinuity. And you'll notice I have this line here, and I have a little hole in the graph. So applying our definition, I can't draw this line without lifting up my pencil to get over this hole to keep going. So that's called a removable discontinuity. And let's look at why that could happen. Imagine we had the graph y is equal to 2 times x minus 2 divided by x minus 2. So consider that graph right there. In fact, that's actually the graph of this, because you'll notice that, do you see how x minus 2 cancels? X minus 2 would normally cancel all the time. And so in other words, in fact, there should actually be a little x right here. And so in other words, this line right here would be going on its merry way, happily ever after. In fact, this equation doesn't exactly match this graph, but that's okay. However, there's one problem. What happens if x is equal to 2? If x is equal to 2, then that means we have 2 minus 2, or 0, in the denominator, which is undefined. And so in other words, this cancels with this 99% of the time, and we get a regular graph. But at that one point, at x equals 2, it's undefined, and so at that one point, we have a little hole right there. So hopefully that makes sense, that this is an example of how we would get a point discontinuity. It cancels everywhere except that point right there, too, in which case there'd be a hole. So if you were curious, if I put parentheses and put 6 plus 2x in parentheses, that graph would now match. But we don't need to worry about that for now. The second kind of discontinuity is a step discontinuity. So let's say I've got a graph and then a little dot right here. So my graph was just moving along, and then it jumped and became maybe even a different type of graph. So you can see that the graph just took a jump or a step. It's called a step discontinuity, where you have a bunch of graph and then it jumps and becomes something else. and goes on its merry way. So those are two different types of discontinuity, a hole or point discontinuity and a jump discontinuity. This graph, by the way, is also called a piecewise graph. And a piecewise graph is where over a certain value of x, it's one type of graph, and then it jumps, and then over a different part of x, it's a different type of graph. So maybe we're a constant graph for a while, and then become an x squared graph or a quadratic graph. So you're kind of going from one parent function to the next on that previous sheet I gave you. So it asks, what is the domain of the graphs above? And so what is the domain? Well, in this point discontinuity graph, the domain is going to be everything except that point right there. And remember that the way we would write that is, for the first graph, it would be negative infinity to 2, but we're cutting out 2, so we use parentheses. So negative infinity to 2, parenthesis, or parenthesis 2 to infinity. So what would the domain of this graph be? Well, in fact, the domain of this graph would be everything. Because if you look, for every value of x, there's a piece of graph that we can attach it to, including right here. This solid point right here means this is the point for the value 2. So the domain of this graph is actually all numbers. So don't mix up domain and continuity. Those are two different concepts. The domain is simply for what values of x does there exist graph. And on this one, it's everything. On this one, we had a hole. Let's see if I can finish this page. Graph the piecewise function below. Is the graph continuous? So here's what a piecewise function looks like as an equation. And so you can see that it's, you always have, either says if or it says for right here. So if x is less than or equal to -1, we're this graph. If x is bigger than -1, then that means y, remember f of x means y equals -5 if x is bigger than -1, y equals x minus 4 if x is less than or equal to -1. So let's graph it really quickly. Let's graph it one part at a time. Let's graph this one because I think this will be easier. It equals -5. So here's x. Remember, x is when things happen. So if x is bigger than -1, then we're equal to -5. So here's x is -1. 1, 2, 3, 4, 5. I'm going to put an empty circle here because we're not equal to. We're only if we're bigger than -1. Y is the horizontal line, -5. Does that make sense? So there we go. So if that's this bottom part, if x is bigger than -1, y equals -5. If we're less than or equal to -1, then we're the line x minus 4. So what I like to do is I like to go ahead and graph this entire line and then just erase where I don't need it. So let's graph the line y equals x minus 4. We have an intercept of -4, and write lightly because we're going to erase some of this. So a y-intercept of -4, and then it's up 1 over 1. Up 1 over 1 because it's positive x. Up 1 over 1. So this is what this line looks like. But this line should only exist if we're less than -1. So it's down 1 over 1, down 1 over 1, down 1 over 1. So here is actually where the line exists, if x is less than -1. So I'm going to erase this. And there we go. So notice that because of the equal sign, it allowed us to fill in this dot right here. And that was very lucky. That usually won't happen. So that was very lucky that we happened to start right here. So notice that that line started at -1. Here's the y-intercept of the line, but it started here, and it's going down this way for x is less than -1. So that's how you would graph that piecewise function. Notice that for less than -1, we're this line. For bigger than -1, we're this line. Is it continuous? Can you draw this without lifting your pencil? Sure you can. So that's very lucky. That is continuous. And so that would be your answer to that part. And again, that's pretty lucky. Most of the time, this is going to happen, where you have a jump and then the graph starts somewhere else. So I think we'll stop there because I'm at 10 minutes. When we get back to part 2, we will do this next problem. Hopefully continuity and a continuous function makes sense because that's a really important idea. See you in part 2.